Hey everyone, by the end of this video, you'll learn patterns that help build reliable applications when integrating with third-party APIs. You will also learn how to prevent unpredictable API costs if you ever decide to deploy something like this to production. Let's get started. So here's what we're building: a financial dashboard that pulls data from 3 different APIs and combines them into a single view. First, we're getting stock prices from Polygon.io. Then, we're fetching financial news from News Data Hub, which provides news article headlines that are relevant to the selected company. And finally, we are using OpenAI to generate a short analysis that connects the price trends with what's happening in the news. Quick disclaimer before we go further: this is purely for educational purposes. Don't use this app to make actual investment decisions. The dashboard lets you switch between 3 stocks. For each one, you get a price chart that shows the past month, a list of competitor stocks, 5 recent news articles, and that AI-generated analysis. The most interesting part about this application isn't what it shows, it's how it integrates with these 3 APIs. Because when you're depending on external services, there is always a chance of them failing, either due to API rate limiting, requests timing out, API server returning 500 status codes due to transient failures, or something else. So let's talk about how we can handle situations like that. Let's start with application architecture. There are 3 main layers: UI, services, API clients. At the top is the UI. This is just Streamlit rendering charts and handling button clicks. It doesn't know anything about APIs or caching. It just displays whatever data it receives. In the middle, we have a services layer, which consists of 2 services: data service and cache service. Cache service handles caching. It saves API responses to disk along with a timestamp. Data service orchestrates the actual data fetching. When the UI asks for stock data, this service decides whether to use the cache or call an API. At the bottom are the API clients layer, which consists of 3 API clients, one for each API we're integrating with. These clients handle the HTTP requests and nothing else. Every API response gets saved to the cache with a timestamp. When the next request comes in, we check that timestamp. If the data is less than 10 minutes old, we just return it from the cache. No API call needed. So if a user clicks through all 3 stocks a few times, the first click on Netflix would be an API call. The second, third, fourth time would be cached data. This cuts the API usage dramatically and preserves your API quota. Now, what happens when one of our API calls fails? What if an API call times out because their server is under heavy load? What about a case when it returns a 500 due to some issue on their side? What if we made too many calls and API is returning a 429? If we do not handle this gracefully, the application might crash, which would make user experience bad. So in order to handle API failures gracefully, we can use retry logic. Depending on what the error is, we can handle it appropriately to ensure our application continues functioning and provides a nice and reliable user experience. We use the retry with backoff decorator on every method that makes an external API call. We use a decorator because it keeps the retry logic completely separate from the business logic. The method that fetches stock data doesn't need to know anything about retries or backoff. It just makes the request. The decorator intercepts any errors that come back and decides whether to try again. If we run into a network timeout error or a 500 error, we retry because those errors typically resolve themselves. If we run into a 400 type error, for example 400 or 403, retrying won't help because this is a client-side error. One exception is 429. We should still retry, but in an intelligent way. When we hit a 429, that means we've exceeded the API's rate limit. Polygon allows 5 calls per minute, which means 1 call every 12 seconds. If we retry immediately, we're just going to hit the same limit again and burn through our retry attempts without accomplishing anything. So we wait 15 seconds between retries. When it comes to a network timeout, we should not wait as long. These issues tend to be transient, so we retry more quickly. Same logic for 500 errors. The server had an internal problem problem, probably temporary, and a short wait is usually enough for it to recover. After 3 tries, if the API calls still fail, we pull data from cache and show it to the user. Even if the data is stale, it provides for a much better user experience than a crashing application. Now let's discuss smart caching and graceful degradation. We have 2 methods for serving the data from cache: get fresh and get stale. One method only returns data if it's fresh, meaning it's less than 10 minutes old. If the data is older than that, this method returns nothing and forces a new API call. The second method returns data no matter how old it is. This is our fallback. Here's how a request flows through the system. First, we check the cache. If we have fresh data, we're done, return it immediately. If the cache is empty or stale, we attempt an API call with those retries I just described. Now, here's the key. If the API call fails after all 3 retries, we don't show an error. We go back to the cache and pull whatever's there, even if it's 2 hours old. The user sees a small indicator saying the data is a couple hours old, but the dashboard still works. They can still see prices, read news, generate insights. The app degrades gracefully instead of breaking completely. Why did we choose JSON files for caching instead of, let's say, Redis or a database? First, it eliminates dependencies. No need to install, configure, and maintain Redis or a database server. Second, setup is simple. Python's built-in JSON library handles serialization and deserialization in just a few lines of code. Third, debugging is more accessible. When something goes wrong, you can open the cache file in any text editor and see exactly what's stored, when it was cached, and whether the data structure matches your expectations. The downside is scale. JSON files on disk won't handle thousands of concurrent users, but for a dashboard with a handful of users, this is a practical solution that works. And one more thing, if you want to change the stocks or add more stocks, you just modify config.py. You add an entry with the ticker symbol, company name, and related competitors. The UI, cache, and services don't need any changes. They read from the config file. Let's talk about a feature that protects you from unexpected API costs: background refresh mode. In the default mode, when a user requests data and the cache is stale, the application makes an API call immediately. This works perfectly for local development or personal use. But there's a problem if you deploy this publicly. Imagine 50 users visit your dashboard at the same time right after the cache expires. Your application would make 50 API calls in seconds, potentially exhausting your daily quota and racking up costs. Background refresh mode solves this. Instead of users triggering API calls, a scheduled background job, like a cron job, refreshes the cache every few hours automatically. You can configure how often this refresh happens based on your needs. Users always get cached data, no exceptions. But here is the trade-off. You save on API calls and keep costs predictable, but users might see data that's a few hours old instead of real-time information. For a financial dashboard where you're not making split-second trading decisions, this is usually an acceptable compromise. This means your API usage is completely predictable. Whether 1 person visits or 1,000 people visit in an hour, you're making the same number of API calls. Your costs stay constant regardless of traffic. Alright, let's wrap this up. When you're building anything that depends on external APIs, expect failures. Network issues, rate limits, server errors, they're all going to happen. Retries handle most of these automatically. Caching isn't just about speed. It's your fallback when those retries don't work. Keep 2 versions: fresh data for normal operation and stale data for when things break. And implement separation of concerns. Put the UI in one layer, business logic in another layer, API calls in a third layer. You can find the full code on GitHub. The link is in the description. There is a full README with setup instructions. If you found this useful, hit like and subscribe. I'll be covering more topics on building resilient systems and working with external APIs in Python. Thank you for watching.